All right, you're all set, man.
Cool.
Okay.
So my name is Charlie Misner, and today we're going to discuss the findings from my research on the seismic response of light frame shear walls with adhesive sheathing connectors. An overview of the presentation. First, we'll discuss some background information regarding light frame shear walls and the use of adhesives. I'll describe the objective of my research. I'll kind of go over some of the connection tests that were done within the frame of my project. Then I'll describe the modeling and the results from adhesive shear walls. I'll introduce a proposed friction anchor system, which is intended to add ductility to an adhesive shear wall system. Then I'll go over the approximate R factors that I calculated during my research, and then we'll discuss the conclusions. So a light frame adhesive shear wall, or a light frame shear wall, is an assembly of several different items. You have studs, a double top plate, and a bottom plate for gravity resistance. You have shear anchor bolts along the bottom for shear resistance into the foundation. Then you have some sort of hold down device in the corners for overturning resistance. And then you also have sheathing and sheathing connectors for lateral shear resistance. So in terms of determination of seismic force, we utilize this equation here, and what we do is we employ what's called an R factor. And so what the R factor does is it allows engineers and designers to analyze their structures as if they are elastic, but take advantage of the inelastic material properties and energy dissipating characteristics of a given structural system. And so the R factor is a function of the system ductility, strength, and redundancy. And the focus of my research was the strength and ductility aspects. So for a nailed shear wall, an R factor per the code is 6.5. And the nail is the source of ductility for this system. So in terms of the use of adhesives, adhesives have been used in areas of high wind for a long time, and they have performed very well. Adhesives have significantly different strength and stiffness characteristics compared to nails, and currently there is no R value published for the use of adhesives in regions of high seismic risk. So the objective of my research, first I determined the P delta, the load deflection properties for adhesive shear walls. I then evaluated these load displacement characteristics for seismic equivalency with nailed shear walls. If I determined that a system was equivalent, then an R factor of 6.5 is justified. And if determined to be inequivalent, then I approximated an R factor. So the testing that was done, here's a rendering of a test specimen that was constructed with 6 different adhesives. And so you had a dimension lumber prism, an OSB cleat, and this was connected with a glue, and then one specimen with nails. And these were loaded in shear in the testing configuration shown. So the results from some of the testing, this is a load displacement curve for the nailed specimen. And so here you see a very large amount of displacement capacity with low strength. High forces were never really seen by this sample. And this is a photo of the failure of the nail, and here you can see the inelastic deformation in the nail. So this curve is kind of representative of 5 of the 6 adhesives that were tested. So there's very little hysteretic response, this blue curve you can barely see, and the envelope curve is essentially linear. And so the takeaway here is that these adhesives have a significantly higher strength than the nail, much lower displacement capacity, and they remain essentially elastic during the entire load course of loading. And here's a photo of a failure of one of these adhesives, and you can see the tear out of the OSB fibers, and this would be characterized as a brittle failure. So one of the adhesives, which a company called Franklin Adhesives titled DF0744-016, which I will refer to as D16 from here on out, actually demonstrated a hysteretic response. So you can see the blue curve here is the hysteresis curve and the gray is the envelope. So here we had a slightly lower displacement capacity compared to the nail, but a greater displacement capacity compared with the other adhesives, and then a lower strength compared with the other adhesives, but higher strength than the nail. So this is kind of the medium ground between most of the adhesives and the nails. And here's a photo of a failure of this adhesive. So here you can see that the failure occurred in the adhesive itself, and this would be, a somewhat more ductile failure when compared with the other 5 adhesives. Summarizing these results, here we have the envelope curves for the 3 different adhesives that I showed earlier, and kind of the takeaway from the different forces and displacements experienced is that the adhesives are significantly stiffer and stronger than the nail, and there was one adhesive that kind of fell into the middle there. So getting into the modeling of the shear walls themselves, the kind of a brief description of the model, I utilized basic frame elements to model the studs, 4 node 6 degree of freedom quadrilaterals to model sheathing. The bottom plate restraint was represented by nodal restraints at locations where there were hold downs or just anchor bolt devices. And this model was subjected to a static pushover, a monotonic racking load. And nonlinear links were used to represent 8-penny nails or the D16 adhesive along the perimeter and also in the field. And so this is the deformation pattern, the deflected shape of my model with 8-penny nail properties applied. And so here you can see that the stud frame displaces in shear, and the sheathing actually rotates and remains mostly rectangular, and then the majority of the deflection and deformation occurs in the connectors. And this is what is expected from a nailed wall. Comparing these results with test data from Selenikovic in 2000, the solid gray line here is my model versus the test data, which is the dotted line. So here you see very good agreement across most of the curve, particularly on the pre-peak load, and then there's a little bit of divergence here towards the end, but this model shows good agreement with test results with a root mean square error of about 1.83 kilonewtons, roughly 9% of the ultimate load. So I felt very confident in this model at this point. Then I applied adhesive properties to my model, to the connector elements, and this is the deflected shape. A couple things to notice is the flexure here in the stud towards the bottom. You can kind of see that the studs are being put into bending. And then also the sheathing element is starting to lose its rectangular shape and resemble more of a parallelogram as opposed to pure rotation and rigid body rotation. Here is the load deflection curve of the shear wall with adhesive properties and nailed properties. And here the takeaway is that this adhesive curve has significantly higher stiffness, so higher strength but lower displacement capacity than compared with the nail, which has a significantly higher displacement capacity and sees lower loads. Taking a look at some of the internal forces in these models, both end stud tension and shear through the thickness of the sheathing were exceeded for the adhesive shear wall. So you can see here that the red line is the capacity of the stud or the sheathing. And then the hold down anchor force was 8.34 kilonewtons for the nailed shear wall compared with, so there's a significant increase in this hold down anchor force, which is a critical detail when designing shear walls. And then overall, this represents about an increase of by about a factor of 5 in the forces that develop in adhesive shear walls when compared with nailed shear walls. So I also examined the effects of anchorage on adhesive shear walls, some brief description of some of the nomenclature. So a fully anchored shear wall, which I've discussed up to this point, has overturning restraint at the corners through the use of a hold-down anchor fastened directly to the end stud. A partially anchored shear wall does not have this hold-down device and has just anchor bolts for shear resistance and also provide a certain degree of overturning restraint. This is the deflected shape of a partially anchored adhesive shear wall, and a critical point in this diagram is at this anchor bolt here, where you can see uplift and pull out and flexure in the bottom plate. These are the load deflection curves for the fully anchored and partially anchored adhesive and nailed shear walls. The dotted lines are the partially anchored and solid lines are the fully anchored. Here you see a decrease in capacity for partially anchored walls of both types. And an important point to note is that for a partially anchored adhesive shear wall, there's no actual post-peak capacity. This curve never actually rolls over. And so that's a problem for the partially anchored adhesive shear walls. And you can also see that the actual anchor force, the overturning force, increased for the partially anchored shear walls, which is also a concern because, as I mentioned earlier, the anchor detail is a critical detail in the design of a shear wall. Evaluating these walls for seismic equivalency, the document, the FEMA P750, includes 4 different parameters for seismic equivalency, and so the one based on strength was met by the adhesive shear walls, but 4 that were based on displacement capacity failed. Also, from a qualitative perspective, the sheathing connector may not be the weak link in an adhesive shear wall, which is also a concern in terms of seismic equivalency. Graphically, what this looks like is that in order for an adhesive shear wall to be considered seismically equivalent, this load deflection curve would need to find its way into this green box here. So at this point, my task came to come up with a way to add ductility to this system. So the way that I did that was with this proposed friction anchor system. And what this friction anchor system is comprised of is a flat steel plate, which is embedded in a concrete foundation, and then a steel bracket, which is fastened directly to the end stud. And so this steel bracket will have 2 pads, which would be made out of material similar to brake pads, and then a bolt here, which would provide a clamping force. So these brake pads would squeeze down on this plate and provide a very precise amount of friction resistance as overturning restraint. And so when loaded, this wall will behave very similarly to a normal adhesive shear wall until the force due to overturning meets or slightly exceeds the force of friction at the anchor, at which point the wall will begin to displace in rigid body rotation and provide ductility and additional displacement capacity for this system. Kind of taking a closer look, what this looks like is that as the wall is loaded laterally, eventually the wall will begin to lift up off the foundation and rotate, which essentially this wall is no longer so much a shear wall as it is a rocking wall system. So to model this, I created a nonlinear finite element that would behave similar to how I felt how I calculated the friction anchor would behave, and subjected it to the same monotonic static pushover analysis. And this is the deflected shape of that. And so here you can see the intended rigid body rotation is occurring in this wall. Taking a look at the load deflection curves of the adhesive shear walls of the different types. Here we have the D16 adhesive shear wall, an 8-penny nailed wall, and the adhesive shear wall with the friction anchor. Something to note is that early on, the adhesive shear wall with the friction anchor and the normal shear wall behave exactly the same. They stay essentially elastic until the force of friction in the anchor is met, and then the wall begins to take off and displace in rigid body rotation, and that's where this additional displacement capacity comes from. So evaluating these walls based on seismic equivalency, the friction anchor system, the wall met all 4 of the different parameters. However, qualitatively, the anchor should never be the governing source of ductility in a shear wall, so these walls are not technically equivalent. So at this point, my task became to determine approximate R factors for each of these 2 systems. So I came up with this simple building model where each floor acts as a single degree of freedom system. Gravity effects are ignored. It was subjected to a static pushover analysis as well as a linear elastic modal analysis. And nonlinear links were utilized in kind of this braced frame sort of geometry, such that each of these 8 foot by 8 foot, 2.4 meter by 2.4 meter sections would behave like a 2.4 meter shear wall with these properties applied. So these are the results from the modal analysis. Here I've shown the first 3 mode shapes of this building, and then also the period associated with the first fundamental mode. So the period of the nailed shear wall system was about 0.34 seconds, and then the period for both adhesive shear wall systems was 0.22 seconds. Some things to note: the reason that the period of the friction anchor and normal adhesive shear wall systems are the same is because in the linear elastic range, these 2 structures behave the same. Also, both of these periods are slightly longer than what is expected, and this is because the effects of added stiffness from building elements such as shear wall or stucco have been ignored. Here are the load displacement curves for the pushover analysis of this system, and these are what would be expected from a system given the description that I provided of this model. And these different curves were then fitted with equivalent energy elastic plastic curves shown here, which provide a way to determine a yield and ultimate displacement for these 2 systems. And so lastly, I gathered data for the fundamental period of ground motion at 7 different locations in the United States that are seismic design categories D, E, or F. So to determine an approximate R factor, I utilized a document titled the ATC-19, which sought to kind of characterize R factors and determine a rational, was the first attempt at coming up with a rational way of determining R factors. So here I took the ductility data taken from the pushover analysis and then combined it with the fundamental period of ground motion and the structural period from the modal analysis into an equation for a ductility-based R factor that I calculated at 7 different locations in the United States. Then I averaged this R mu, this ductility-based R factor, and came up with an average R mu for each of the systems. And then I adjusted the R for the system based on the difference between the ASCE 7. And these were the results. So the R factor for the nailed shear wall system is obviously 6.5. An R factor for the adhesive shear wall system is about 2.0, and an approximate R factor for an adhesive shear wall with friction anchors is about 6. So some of the applications in future research: the added strength of the adhesive shear wall system kind of opens the door to leaner, more cost-effective lateral force resisting systems, and this opens up some new additional architectural options in a light frame building. Further research is needed to kind of characterize and lock down the behavior of this friction anchor system. And then the R factors that I determined are approximate, using the approximate ATC-19 method. But the findings of this study lay the foundation for a potential FEMA P695 study, which is kind of a probabilistic method for determining R factors for buildings. The conclusions of my research: adhesive shear walls are significantly stiffer and stronger than nailed shear walls. An R factor of 6.5 is not justified for light frame shear walls with adhesive sheathing connectors. And it is possible to devise a conceptual friction anchor system that adds ductility to adhesive shear walls and improves the seismic performance. And then an approximate R value for an adhesive shear wall system with normal hold down devices is about 2.0, and with friction anchors, this R factor is about 6.0. And lastly, one thing that I learned over the course of my research is that just because something doesn't do what you planned it to do doesn't mean that it's useless. Thank you.